So for this one, you're asked to show the momentum of a photoelectron. Momentum of a photon of AM radiation and wavelength is given by this equation, where h is the Planck constant. Okay, so this one, you kind of like need to think about certain equations that can combine to get your Planck constant equation. For example, if I want to include wavelength, most of the time I will need to use the equation for energy of photon. E is equal to hc over lambda. Okay, and then also at the same time, the momentum P, because it's half mv squared. It's mv. This is the energy of the photon. I want to see if I can get rid of the value of C. There is a lesser known equation, which is momentum P is equal to energy over the speed of light. I guess we can use this. Because then can put in hc over lambda divide by c. So this is h over lambda. Okay, so this one is 1 mark. And then you show the algebra leading to the answer is the other mark. Okay, moving on to part 2. Use the expression in A1 to show that a photon in free space has a momentum of this much. It's a photon of red light. And use the equation. P is equal to h over lambda. 9.5 times 10 to the power of negative 28. 6.63 times 10 to the power of negative 34. I'm going to find lambda first. If you press your calculator, lambda is 698. So if you remember your electromagnetic spectrum from 400 to 700 nanometer, this is U. This is violet all the way to red. So this one is good enough, lah. Close enough to 700. Very close to 700. So you can just write an explanation here. No? This is in the red wavelength range. You don't need to, I guess they expect you to know. Oh, okay. No? If you don't know, you just find lambda and hope for the best. Okay, so B, a beam of red light is incident normal to a plane mirror. Oh, okay. As shown as in figure 8.1, the momentum of each photon is the same value, 9.5. So we're going to shoot some red light into the mirror, like a laser, question mark. All of the light is reflected by the mirror in the opposite direction. So the light come like that, then the light come back this way. Okay, the cross-section area of the beam is this much. Show that the number of photons incident on the mirror per unit time is given by this number. So, you know, you have power, right? So power is intensity over area. So I can put in the power. And the reason why I want intensity over area is because intensity is the, I guess I can put in power is energy over time. Do I have the frequency, the wavelength? I have the momentum, but I also have the wavelength. Maybe I should use that instead. Okay, let's try both. Oh, okay, so this is total energy per unit time. Number of photons multiplied by the energy of one photon. So this will be HF divided by T. So the total energy would be the number of photons multiplied by energy of a single photon divided by time. But instead of HF, maybe I'll use HC over lambda, because I have HC over lambda. All right, so the power is 160. Oh, wait, the intensity is 160 watt per meter squared. Okay, which means I need to substitute 160 watt per meter squared divided by area 2.5 times 10 to the power negative 6. Okay, throw everything inside. 2.5 times 10 to the power negative 6 n over t, big bracket, h c over lambda. I have h over lambda. But h over lambda is momentum, right? So can I use momentum? I mean, feel free to use hc over lambda, but I also have momentum. So 9.5 times 10 to the power negative 28. Times 3.0 times 10 to the power. H over lambda is P. That's how you get the equation E, energy is equal to PC. So it's like you have E is equal to Hc over lambda, energy of photon. You also have wavelength of photon, P is equal to H over lambda. So because of this, somewhere in between here, your E can also be equal to PC. All right, so if you put everything together and poke your calculator, you'll be able to get the number per unit time as 1.4 times 10 to the power of 15. So this is a familiar question. You've done it before in your trials. The only difference is that you were given power back then. Now you need to use power is intensity over area to find power, then throw it inside the equation. Okay, so it's not or, it's a total. Okay, so where are the marks? If there's an understanding that power is intensity over area, either the equation or the substitution, 1 mark. Okay. The other one is you putting it into the energy over time equation, the substitution, and this equation. It's 1 mark. All right, use the information in B1 to determine the pressure exerted by the light beam on the mirror. To find pressure, P is equal to force. Pressure and power is not the same thing. They have the same symbol, but they are not the same thing. Okay. So to find pressure is force per unit area. But to find the force, let's find force first. It is the change in momentum over time. So let's consider your light beam. Your red light will come here with a momentum of 9.5 times 10 to the power negative 28. What unit did they use? Newton. Yeah, Newton second. NS. But then it will reflect with negative opposite direction, what? 9.5 times 10 to the power negative 8 NS. So to find the change in momentum, I will take 2 times 9.5, or if you want, guess you want to show everything then, 9.5 times 10 to the power negative 28 minus negative 9.5 times 10 to the power negative 28 also can now. Times 2 also can. Divided by T. So I'm going to put this one inside here. Pressure is, but this is how many, this is the force in one particle, one photon. So we will need to multiply by 2. 1.4. Okay, anyway, this will be, let me put everything together first. 2 times 9.5 times 10 to the power negative 28, the momentum, change in momentum, multiply by the number of photons, divide by time. Okay, so this one, this whole thing is the change in momentum for 1 photon. Okay, but we don't have 1 photon now, we have many photons. To be specific, 1.4 times 10 to the power of 15 photon every second. So this one here, for this one, divide by area. So this is change in momentum over time for n photons. Change in momentum over time for n photons. Okay, this one over T, this one over T. N photons. N. So the total force, because you have many photons. Of course, you can put everything together, but you can also do it separately. This. Okay, time to throw stuff inside the equation. This will be 2 times 9.5 times 10 to the power negative 28 times n over t. N over t is 1.4 times 10 to the power of 15 divided by the area. So the area is 2.5 times 10 to the power of negative 6. So if you press your calculator, you will get 1.1 times 10 to the power of negative 6. So let's recap what we did in terms of calculation. All right. We know the intensity or the brightness of the light, and we know the momentum of every single photon. We also know the cross-sectional area of the beam. And the first part requires us to find how many photons hit the mirror in 1 second per unit time. So we know power is a total energy over time. So I can take the number of photons multiplied by the energy of 1 photon per unit time. But I also need to substitute power, and power is intensity over area. So putting everything together, I find how many photon collides with the mirror surface in 1 second. And then I want to find the pressure. So pressure is actually force per unit area. But to find the force, I need to consider the change in momentum. So the change in momentum need to multiply by 2 lor, because the photon go in and go out, reflect. Okay, so this reflection is new. Last time the photons are absorbed. If they're absorbed, then it will be 9.5 times 10 to the power negative 6 minus 0. So if let's say instead of a mirror, I replace this with a absorb. If your photons are absorbed, maybe a black color paper, then the momentum here is 0 because it doesn't reflect. So your force will don't need to multiply by 2. It's just 9.5 times 10 to the power negative 28 over t. This situation, photon is reflected. That's why the momentum have to times 2 because go and come back, divide by t. I can press calculator lah, but then I don't know t ma. I need to combine it with n over t, so I'll just leave it first lah. This one is equivalent to multiply by 2, but this is for 1 photon. I have n photon. So n photon per unit time will give me this 1.4 times 10 to the power of 15. Okay, n over t. I also have the area. I can put everything together to find the pressure. It's very small. Right, so part C. The beam of red light is now replaced by a beam of blue light with the same intensity. Suggest and explain whether the pressure exerted on the mirror by the beam of blue light is less than, same as, or greater than the pressure exerted by the beam of red light. Okay, so blue and red, the only difference is wavelength. Okay, we still have the same intensity. So let's brain first. Which wavelength is shorter? Blue. Or maybe I'll just compare R and B. So I need to draw a table now. Wavelength of blue is shorter than wavelength of red. E is equal to hc over lambda. Energy of the blue photon is less than the energy, more than the energy of the red photon. Okay. Shorter wavelength, greater energy. Then I go back and stare at my calculation. If this energy is bigger, right, this wavelength is bigger, but the intensity is the same. So intensity the same, power the same, hc over lambda is bigger, n over t will be smaller. So let's put that together. Intensity is power per unit area. Power is intensity times area. But also, power is total energy over time. So power will be the number of photon multiplied by energy of photon over time. I guess you can put it together if it's helpful for your brain, although it's not necessary. I times A is N, energy of photon over time. Okay. Area is constant. Intensity is kept constant. Same intensity. Energy of photon for blue increases. Okay, blue is greater because I replace red with blue. So if energy of photon increases and I want to keep the other side constant, what happens to the number of photon per unit time? Decreases. Okay, I think several of you have already asked the question multiple times in many different ways. So it's important to understand that intensity, if intensity is kept constant and I need to make larger photons, then I cannot make that many photons, got less photons per unit time. Okay, so can just say that the photons have greater energy so because of this there is less photons incident on the mirror per unit time. Okay, but we need to bring it to pressure. Let's look at the pressure. Pressure is change in momentum over time. Okay, divided by area. So you gotta look at the calculation here. So I think I'm just gonna draw a line here and just write down the calculation that I did. So pressure was change in momentum, or rather 2 times the momentum of the photon times n over t divided by a. This was a calculation I did just now, after some grooming. Okay, this 2p not the same p. This p is momentum. This p is pressure. Okay, most of the time pressure I will keep small p but okay. Now not that you can tell from the way I write my p's. Is there a difference? Okay, never mind. Let's look at this equation. Okay, so constants we like. This 2 is constant. Pressure is not constant. Area is constant. We want to see how it affects pressure. Okay, n over t decreases. Less photon per unit time. But what about the momentum? Momentum of the photon is h over lambda, right? So right now, my lambda blue is less than lambda red. So momentum for blue will be greater than momentum for red. Hiya. So what happens to this momentum? Increase. Do they increase by the same amount? Yes. Why? Because of the inversely proportional to lambda. See? So does pressure change? No. Pressure, no change. Because if let's say you here, you decrease by a factor of 4, here you will increase by a factor of 4. They affect each other in the same way. Okay. So you can try and put values in if you want to convince yourself, but it's only 2 marks, so I will refrain from doing so. The greater energy, less photon incident on the mirror per unit time. But the photons also have greater momentum. Since momentum is equal to h over lambda, and I can rearrange this but really it's not needed. N over t is equal to I times A over energy of photon. So the IA hc over lambda is down here. But the momentum is h over lambda is up here. Might as well just put everything together. Okay, so I put this one inside. Momentum is 2. The pressure, see, even I'm confused. Pressure is equal to 2. Momentum is h over lambda. N over t will be IA over hc over lambda divided by A. My whole point of doing this is to show you that the hc over lambda, the h over lambda and the h over lambda will cancel. That's why although lambda decrease, this one increase, the number still decrease. Okay, so these two will cancel. That's the point of this, me showing you this now. Okay, but regardless, it's just one mark. This is the type of mark that we want to squeeze the students. But anyway, photon have greater momentum since P is equal to h over lambda, and N over T will be equal to number of photons per unit time. Do I want to write this? Nah, I don't want to. P equal to h over lambda. Just write the E one. Energy is this. Both momentum and number of photons per unit time changes by the same factor. So pressure remains the same. Yeah. This is it. So photon has greater momentum. You don't really need to justify the factor is the same because they didn't give you any information for you to show that working. But this part here, look. 1 mark is when you mention photon have greater energy. So less photon incident the mirror per unit time. Because you can definitely write this one. Or you mention photon have greater momentum. Okay, 1 mark. Second mark, you can just mention that the pressure is the same because both momentum and the number of photons per unit time changes by the same factor. If I got space, I will say momentum increases and number of photons per unit time decreases by the same factor. So 1 increase, 1 decrease by the same factor. This one is 1. Yep, this is a hard one.